All right, so again, this is kind of more of a typical type of question where you'd be using linearization to answer the question. Find the equation of the tangent line for this function at this point in Taylor form. Now, on an AP test or my test, I'm not going to tell you the form to put it in, but again, that's kind of the form that we are accustomed to writing from the beginning. So what do I need for the equation of a tangent line? Two things, slope and a point. And as long as I have a function and an x value, that's really all I need to make everything happen. So let's go ahead and find the point first. It's going to be the y value at E is the y coordinate I need. So that's f of E, which is the natural log of E, which is 1. Yeah, good. So the point that we're using is the point E comma 1. So I'm halfway there. I got my point. Now I just need the slope at the point, and that's the derivative. So before I can find f prime of E, I need to find f prime of x. And go ahead and get in the habit of showing that even if it's a real easy function, like the natural log of x, what's its derivative? 1 over x. And then f prime of E, you get 1 over E. So notation, and what's the third one? Location notation. Right. It matters where you put your notation as well. If you put f prime of E over here, and they don't have that, then that's not the right location for your notation. So we established that it needed to be in the right spot. Okay, there we go. Good. Now, if you want to call that e to the negative first, that might be another form that you prefer. Whatever. I don't care. I'm going to leave it as 1 over e. So here's the equation. And we get y, but it said to, well, it didn't say. It said to call it L of x. Because we're going to use it down below, I'll go ahead and give it a more suitable name. And it's going to be the y value 1 plus the slope 1 over e times x minus e. Just be very diligent when you're writing the equation of the line, when you have your ingredients in front of you, right? If the recipe calls, like for flour before eggs, don't put eggs before flour. It's real easy to kind of put your ingredients in wrong, right? I've seen a lot of people kind of put the slope here instead of the y value, or put the y value there instead of the slope or something. All right, so now that we have the equation of the line, that takes care of part A. And you would get bukus of points for that, for following the directions and coming up with the right answer with the right notation and the right location for your notation. All right, so part 2, it says use the equation of the tangent line to approximate the natural log of 3e halves. And then is it an over or an under approximation? Does anyone know off the top of your head what the natural log of 3e halves is approximately? I don't know. I could expand it, right? That's the natural log of 3 plus the natural log of e minus the natural log of 2, using the rules of logs. And, of course, what's the natural log of e? 1. So it's really 1 plus the natural log of 3 minus the natural log of 2. And I can condense the second part and call it the natural log of 3 halves, or 1.5. So it's really 1 plus the natural log of 1.5. Boy, that looks a lot better, but what's the natural log of 1.5? Yeah, I don't know. Okay, and then I add 1 to it, and I know it's 1 bigger. So I know it's at least 1, right? Because the natural log of 1.5 is positive or negative? Positive, right? The natural log of anything greater than 1 is going to be a positive number. So I know it's going to be bigger than 1. All right. I want to do better than that. So here's the idea. In the neighborhood of the point of tangency, which we can say is the center of the approximation, as we saw yesterday from the graph, near the center of approximation, that is near the points of tangency, the tangent line is a decent approximation of the function. Now, if you think about what we're doing, it's kind of good to get a visual description here. The natural log of x looks like this. And notice, like yesterday, it increases at a decreasing rate. That's kind of nice. We are centering our tangent line right here at E, which is about 2.7. So what we just did is we wrote the equation of that line. And I'm trying to figure out what the value is. This is 1e, remember, and I'm trying to figure out what it is at 3e halves, which is the same as 1.5e. Yes? So I'm only a half of an e unit away, about right here. So this is the actual value that I'm interested in finding. That's what I want. But that's really hard to evaluate. I have the equation of the line, which is a lot easier to work with. Maybe I can just use the pink values. I can use the pink values number as an approximation of the function values number. And now, Brandon, we know from the graph that our approximation is going to be a what? Under or over? It's going to be an over, right? And we're going to have to justify that without just saying because look at the graph, right? So let's see what we can get here. The notation is pretty important. The function ln of x was called f. So here's what you'd want to say. You either say f of 3 e halves is approximated by L of 3 e halves. You could do that. Or you can actually say the natural log of 3 e halves is approximately L of 3 e halves. Either one. But once you do that, then you put equals, and then you plug that in to your Taylor form, which is a lot easier version. So 1 plus 1 over e, 1 plus 1 over e times, we get 3e halves minus e. Now, on a free response, I guess that is an exact answer, but we want to keep going. What is 3e halves minus e? 1/2 e, right? Yeah, or e halves. 1/2 e. What happens with the 1 over e times e over 2? They divide out, we get 1/2, and 1 plus 1/2 is 1.5 or 3 halves. There you go. So apparently the natural log of 3 e halves is about 1.5. Now we know it's an over approximation. We are going to have to justify. Now if you have the graph, you could say since the graph is concave down, okay, so let's go ahead and state that. L of 3 e halves over approximates f of 3 e halves since, and then here's one argument, since f of x is concave down, where is f of x concave down? Certainly over the interval that we're dealing with, right? From 1 to 1.5e. But again, if you want to just categorically say it's concave down everywhere to the right of 0, for all x greater than 0, that covers the interval. It has to at least be on the interval that you're working in. So that's one way to do it. If you're not sure what the graph looks like, because sometimes we'll be doing this with functions that we can't just sketch it and see what we're doing, we can still analyze the concavity, right? But we would need to look at the second derivative. So let's come back up here to part A, and let's go ahead and find the second derivative. 1 over x is the same as x to the negative first, yeah? And the derivative then would be negative x to the negative second, also known as negative 1 over x squared. And so if we did this down below, I'm just going to keep the argument going over here. Negative 1 over x squared is what? Positive or negative? Negative for all x where? This is where you'd have to be careful. If you just look at this equation, it's oops, I didn't put less than 0. You do have to be careful. It's less than 0 for all x. You don't want to say for all x not equal to 0, because that's where it's undefined. But if you do that, then you're including negative numbers, right? And remember, our graph is just positive numbers. So for all x greater than 0. This would be the justification that you could put down below. Let's copy it. So number 2, right there.
If we just put f times less than 0 for all, maybe left out the actual
computation, if it's not given and you're referring to the equation, you kind of need to have it there. Yeah. Otherwise, refer to the concavity of the graph of f, because then you're never really making a claim about the equation. Yeah. In other words, if you say it on faith or you did it in your head, it's probably best just to show it for the equation. Yeah, good question. Okay, there you go. Either one of those works. Any questions on section 3.7? This again is a more typical type of question. Let's see what it actually is. That'll be kind of a nice way to end this. We know it's 1.5 for our approximation, but the actual answer is going to be, again, something what? Bigger or smaller? I forgot. Smaller. So the natural log of 1 point, my decimal's missing on the key. There it is, 0.5. And if you just want E, you can hit second division instead of second ln. It's just E the number. Yeah, it turns out to be 1.405, which is not bad. We're off by a little more than, or a little less than a tenth. Yeah. Yeah.
On the worksheet, one of the problems asks you to graph delta x and delta y. For 9 seconds, and I didn't quite understand how to do that. It's a sketch of.
Oh, yeah. You could skip that part.
I just want to know how to do it.
Okay, I will explain it. Yeah, let me stop this recording here.